Principles of Operating Systems, Chapter 1. The computer system consists of several hardware components, processors, memories, system buses, storage devices, input devices, output devices, and software. Lots of software. All of the software can be considered as being either operating system software or application software. The operating system is particularly important. It has several functions, including controlling the access to the processors, provides a set of services to users of the system, and controls how they interact with the system, and it manages the system hardware components. The primary function of a computing system is processing data. The operating system manages hardware components in the system. Generally, these hardware components will include processing units, memory, various names, input devices, output devices, external storage devices, communications devices, and system buses. The operating system has several functions. It uses the system resources and controls access to the resources. It provides a standardized set of services for the system users, and it manages secondary memory and I/O devices. It controls the operation of the computer, and it performs data processing functions. And its I/O modules provide control of movement of data between the computer and external environments. Those include storage devices, communications equipment, and any other I/O devices. The system memory is divided up into a number of cells, and each cell has an address and number. Cell number 1, number 2, number 3, so on. The contents of some of the cells will be codes for CPU instructions. The CPU has a register called the program counter, and the contents of the program counter are going to be the address of one of the cells in the memory. What the computer system does is it cycles through, keeps repeating 3 steps. First, it copies the contents of the cell whose address is in the PC. Then it increments the number in the PC so that next time we come through, it'll have the address of a different cell. And then it executes the instruction that it just copied. Most of the students are going to be familiar with the term operating system and probably would be able to name some of the operating systems: Unix, Linux, Windows, Android. many, possibly most, of the students would have problems in describing just what an operating system is. Well, here's the answer to that question. An operating system is a program or collection of programs that manages the resources of a computer system and provides interfaces between users, hardware, software, and peripherals. Operating systems are some of the most complicated pieces of software ever developed. An operating system is going to include subprograms that provide interfaces. Interfaces between users and hardware, interfaces between users and software, interfaces between software and hardware, and interfaces between software and other software. The operating system provides a number of services, including programs like editors and debuggers that help in the development of programs, means for loading and initiating execution of programs, control of the access to input-output devices, protection of information, controlling access to files, control of system access, control and detection of errors, identification and response to errors, and statistics useful for keeping track of the utilization of the various resources. In our modern world, they're continually developing new kinds of hardware and new kinds of software. Any computing system is going to be incorporating some of the newer hardware and or software at various times in its lifetime. So to be successful, an operating system has to be capable of evolving to deal with changing system environments. By modern standards, the early computers were basically calculators. The programs, such as they were entered by setting switches, connecting wires, and output was in the form of patterns of lights illuminated on a console. Just setting up a program, entering the program, getting it ready to run would take a lot of time. They would only run one program at a time, and so the users would access one after another. The installations would have a sign-up sheet to reserve the computer time. Of course, there were always going to be scheduling problems. Sometimes a program would run faster than anticipated, and the next user wouldn't be available for a while. Sometimes it would take longer than anticipated, and the next user would have to wait a while. But very, very often, the computer would be sitting, not doing anything for a long time in between runs. This system is slow, inefficient, and lots of errors got made. Now, the computing systems were expensive. People who invest a lot of money into a machine like to see it used as much as possible. They don't like to see their investments sitting idle doing nothing. They like to see their computers producing lots and lots of output. Efficiency and speed were the main motivating factors for most of the early computer development. The first major step toward the development of operating systems came when John von Neumann described a system with programs and data stored in computer memory. These programs then can be read into computer memory as a bunch of punched cards or a paper tape, and then executed from RAM. This motivated the first primitive operating systems. These were developed in the mid-1950s. Basically, they were supervisor programs, resident monitors, that provide basic I/O operations, controlling punch card readers, paper tape readers. A machine can read a deck of punch cards a lot faster than a technician can throw a sequence of switches to enter the code for the program. With this system, then, the system operators can just put in a batch of programs into the card reader, and the system will read a program, and then when it finishes that one, it reads the next one. When it finishes that one, reads the next one. These are batch processing systems. The system reads a program, executes it, then it reads another one. It doesn't have to wait for the operator to intervene and enter a new program. It just reads the next bunch of cards. It was almost immediately recognized that user programs shouldn't be able to interfere with the memory that was occupied and used by the resident monitors. So systems were set up and designed to operate using different execution modes. A user mode, where normal user-written programs would execute, being restricted to memory with where user programs and data would reside, and a kernel mode for operating system use. This would have these programs executing in kernel mode would be less restricted, have more rights, be able to access memory that user programs would not, and would be able to execute a wider range of program commands than would be normal user programs. Now, an operating system clearly adds extra overhead to your computing system. Operating systems, after all, are programs. They occupy space in memory, and they take time to execute. But they aren't application programs. They themselves support user programs, but they don't while executing do user-defined operations. Nevertheless, even the simplest serial batch processing systems ended up as major improvements in efficiency and especially throughput for the computing systems where they were executing. Pretty soon, somebody figured out that most programs don't use anything like all of the computer memory available, and would be usually be possible to put more than one program into computer memory at the same time. If you do that, when one program finishes, the system can start executing the next program right away. There's no loss of time waiting for another program to load, since the second program is already in memory. Of course, a system like this requires supervisor programs a lot more sophisticated than the ones with only one program in memory. You have to keep track of where each program is located. You have to know where to start the next program executing, but also you have to avoid overwriting other programs in memory. In addition, when a program is done executing, the system has to select which of the waiting programs to start executing next. As computers started using larger and larger collections of data, people started turning to external data storage in order to handle these larger collections of data instead of having all in RAM at the same time. This, of course, requires more complicated operating systems to provide better interfaces for external devices. Now, when a program accesses one of the external devices, execution of the program has to pause and wait for the data to be copied into memory. Now, the external I/O units were slow, and waiting periods were taking a higher toll on the system efficiency. Given that lots of systems at the time were loading several programs into memory, the next step in design was a system that would switch control to another program whenever the program that's executing had to pause for data input-output. This way, the processor would be in pretty much continual use, and we get systems that were even more efficient. Of course, the operating systems to do all of this had to be even more complicated. The system has to identify when the I/O operations were done and which programs would be ready to proceed with their execution and which ones were not. It was this kind of need that led to the development of interrupt processing. Interrupt processing then allows programs to return control to the operating system when they are pausing to wait out for an I/O operation. It soon became common for programs, complicated programs, to be subdivided into relatively independent units. It's particularly true of operating systems, since operating systems are so complex. But it was also true of other kinds of programs, because complex programs were simply becoming more and more common. So it became common to talk about complex programs as being divided into things were called processes. A process is an entity that can be assigned to and executed on a processor. A unit of activity characterized by a single sequential thread of execution, a current state, and a set of system resources. So the process has three components: code that can be executed, data that the process will use, context, process state of the program. The context is important because that's the internal data by which the operating system is able to control the process. The execution context includes contents of the registers and other information like priority of the process and its state, whether it's waiting to execute or if it's paused or if it's waiting for input-output, and if it's waiting, the identification of the event that would allow it to continue. Now, it also became common to talk about threads. A thread of execution, is the smallest sequence of programmed instructions that can be managed independently by the scheduler. Threads are different from processes in that a process is independent, but a thread is a subset of a process. It can only work within a process. Processes involve state information, more state information than does a thread. Multiple threads within a process can share the same process state as well as memory and other resources. Processes have separate address spaces. Threads share address space. Processes interact only through system-provided interprocess communication mechanisms. Very quickly, people realized that when you let several programs occupy memory at the same time and move from one program to another, one process to another, when one is paused for input-output, this brings about a change in the way that they would evaluate the performance of a computer system. With only one program at a time, when you have to finish the program before you start another, then the emphasis is on getting each program done as quickly and as efficiently as possible. But when you can move from one program or one process to another quickly and easily, then what becomes more important is how many programs can be finished in a given time period, rather than how fast one program can be done. About the same time that this realization was taking place, the price of RAM was coming down, and so systems were using more and more RAM, larger and larger amounts of RAM, and that lets more and more programs or processes to be in memory at a given time. With the change of emphasis came the realization that compute-bound programs tended to block progress of other programs. That is, a compute-bound program could simply take over the CPU and not relinquish it. This gets that one program done, but it doesn't help the progress of other programs. I/O-bound programs, on the other hand, spend a lot of time simply waiting for data to be transferred. They don't make use of the processor for very much of the time when they are active. A computing system then can support many more I/O-bound programs, since most of the time they are sitting and waiting. Now, in order to permit more I/O-bound programs to proceed, they started designing systems that would force the compute-bound programs to let the I/O-bound programs function from time to time, dividing up the time into time slices, okay? Assigning a process a slice of time, and if they came to a pause, fine, reassign the processor to another process. But if they used up all of the time, pause it and let another process proceed. This way, the many more programs or processes could be working at a given time, and you get more programs completed. It pretty soon occurred to the system designers that it would be convenient if the users could interact directly with their computing systems. Up to that point, the system was for the users to write their programs and put them on in a deck of cards or paper tape, hand them over to system operators, and then come back the next day to get the resulting output. Now, teletype terminals were becoming quite common, and they provided a very convenient means for communicating with computer systems. Direct human interactions tend to be input-output intensive, since humans function so much more slowly than computers. Even quite a large number of simultaneous users online would actually do not add very much to the CPU load, since interactive user programs tend to spend most of their time paused waiting for users to enter something. So they designed interactive support systems that allowed users to write to compile and execute their own programs directly online from these computer terminals. This, in fact, turned out to lower the operational costs, since they didn't need nearly as many operators, personnel, for loading and distributing programs and data. The users now were starting to do that from their terminals directly. This also, of course, opened up the computer access to a much wider group of people, many more users than before. The introduction of interactive multi-user systems, we're creating situations with more and more programs in a suspended state, waiting for user input, and at the same time, external storage systems were being developed that had access times, although they were a lot slower than RAM access for the computers, were, from the point of view of a user, essentially instantaneous. Now, these external storage systems were much cheaper than RAM, and so it was recognized that they could accommodate even larger numbers of users, and therefore larger numbers of programs executing, if these suspended programs could be stored on the larger and cheaper external storage systems on disks. Virtual memory systems then were developed to do just this, to store the contents of RAM that weren't likely to be referenced immediately on external storage and brought back into memory when they were ready to be executed again. Now, of course, these virtual memory systems were more complicated than the previous systems, and that required operating systems that were bigger and more complicated. These operating systems have to identify which program segments were likely to be referenced soon and which were not. They had to keep track of where on the disks that these segments were stored so they could be retrieved immediately or quickly when needed. And of course, they had to locate space in RAM to put these externally stored suspended systems. And they had to be retrieved and stored in a way that was compatible with the other segments of the same programs already in RAM. And of course, it had to be done quickly enough that the users would not notice significant slowdown of execution. Virtual memory can be an effective strategy, principally because of the principle of locality. Basically, this is that any memory references by the processor will tend to be close to the next or the previous memory reference, that these references tend to cluster together. Most programs have sections of code that is sequential. One command executed after another command executed by another command. And the codes then are going to be one after the other in memory, close together in memory. In addition, lots of computer programs involve iteration, repetition of the same section of code again and again. Data very often is stored as an array with the data elements stored sequentially. And the programs that reference these data tend to reference them one after another in sequence. So as a general rule, when a program references something in a given location in RAM, it's likely that the next few memory references are going to be to entries in locations very close to that location. If, for a reasonable period of time, none of the cells in a particular section of memory have been referenced, then it's likely that several more memory references will be to other sections of memory. So sections that have not been referenced are likely to not be referenced, so that you can swap out some sections that haven't been referenced, and the system performance is not going to be affected, at least not immediately. Now, locality of reference is not quite as pervasive as it used to be, principally because object-oriented programming tends to make use of large numbers of small functions, and data structures like trees and hash tables tend to result in chaotic memory reference patterns as opposed to array data. New technology was being developed that would permit the creation of RAM that was faster. Unfortunately, faster RAM was also more expensive, used a lot more power, and produced a lot more heat than standard RAM technology. It was not cost effective then to build computers using all high-speed RAM, but it was reasonable to build in small sections of high-speed RAM, caches. When the processor would reference a cell in normal RAM, then the section containing that cell could be copied into the cache, and principle of locality indicates the next several memory references were likely to be used the same high-speed RAM in cache instead of regular RAM, and so could operate a lot faster. So that using only a small amount of high-speed RAM, you could end up using most of the operations with high-speed RAM. Of course, that means that your operating system now has to keep track of what is where, which sections have been referenced recently, which cache cells have had their contents modified, which ones have to be copied back to RAM before replacing them. Now, there are lots of programs that do a lot of writing to disk, that are disk bound. These kinds of programs are slowed down a lot by the relative slow access times for hard disks. Slow compared to RAM access and CPU operations. Of course, the locality principle applies to disk access just like RAM access. So in order to speed up the progress of these kinds of I/O-bound programs, people started designing systems that would keep recently retained RAM, recently referenced sections in RAM rather than putting them onto disk.